Hello, this is Jun-Sung Ro from Post-Tech Korea. Thank you very much for inviting me to the flat optics workshop. But unfortunately, I have some time conflict with my relocation from United States to Korea after my sabbatical leave. So sorry to provide this recorded video. So I hope next time we're gonna meet together. And today I'm going to talk about two parts: is manufacturing, so larger scale, and material side for like a visible shorter frequency optical metasurface. So mainly I will talk about some new 3 material: particle embedded resin (PER) and low loss amorphous silicon and their related family, and hybrid ALD structural resin we recently developed. So or the motivation, we are in the flat optics community, so I hope you already all understand why we need this smaller, compact, lighter optical component and device in many different fields. So mainly, combining with the electronics device, these photonics can do huge role, for example, in LiDAR and all the extended reality device in the future. So well known, this is a feature of the metasurface. And this is one example we published in 2019. This is a conventional near-IR infrared camera lens, so convex lens. So we like duplicate the same spec, same function with this metasurface lens. You can see the comparison of the thickness. And if you zoom in, rather than making this curvature of this glass or plastic, here a lot of the silicon nano rod array is located here. So this is some representative example what we need to do. So controlling the wavefront and control the phase, amplitude, and so on. So for example, if you want to making this focusing like convex lens, we make this phase encoding into this 2D meta surface, making quadratic phase information, so and so on. So we can do many interesting thing. So pioneered by this chair, Professor Capasso, so a lot about this meta surface, meta lens, and later this active device in from many different group. And like another co-chair, Professor Dr. Chen and Professor Fan contribute a lot of this freeform lens design and fabrication, manufacturing, and so on. So simply, this is what we need to do. So we need to consider final application. So let's say we're gonna do lens or we're gonna do holography, and we decide what we need to control. Like we're gonna control the phase, we're gonna consider polarization, and then we consider what type of atomic design, so what type of meta atom will be chosen. For example, this rectangle will control the circular polarized light for something. So, and then what type of material should be used that is related to the usually frequency range we're going to operate. So this is from design to material selection, functionality, and final application science. So simple, some like process chart. So one recent example, what we can do. So many example in the field, but this is our Face ID dot projector or structural light imaging. So we reproduce like Apple's Face ID same function, 10K dot into the 2D space, and the size become like 10 times smaller than this Apple's Face ID or Samsung's this dot projector. So it can be used like face recognition, object detection, or 3D depth sensing or mapping. So people say this is short distance LiDAR, less than 5 meters, or just dot projection or point cloud generator, or structural light imaging. So this is one example, invisible, using TiO2, but this is not a regular TiO2. I'm going to talk later. TiO2 particle embedded resin, and it's about very small size of 300 micrometer, spread out or the 10K dot into the 2D space, or we can do like a 4D space, like half go to transmission and half back to the reflection. So anyway, after making this dot and object detection by the stereo camera, and we do image processing and make a object detection and make a 3D depth map. So this is one example, and we can do like not just an array of dot. We can do change of this structural light into the 2D array, 1D array, and many different shapes. So now the challenge is how we can extend the range of the detection. So not just rather than using high power laser, can we increase this transmission and can go further, like 15 meter for AR glass, like a middle distance LiDAR. So that may be challenging, as existing still. And this is another example inspired by this Professor Capelso's work in OCT. This is a similar concept, but meta lens is integrated to the endoscopic this fiber optics. So you can see the 3D printed fiber, the meta lens fabrication directly onto the fiber. So this is use the 3D printer to photon lithography. So the size of the pattern is a little large, so it's work for near IR, so not invisible. But anyway, this metal lens on the endoscope, what they do is a correct aberration. You can see from 1250 to 1650, they correct aberrations comparing non integrated this fiber. They have a blurred image, but metal lens integrated, achromatic metal lens integrated fiber has a better, much clear image. So rather than we change everything in the at once, we can consider what type of metal lens component can contribute, like improve the current optics. So maybe some say it's incremental, but optics, many different imaging device, many different optics. So they appreciate their performance improvement because they couldn't solve many issues from conventional optics. So that's our some direction and motivation. But here, 2019, this World Economic Forum, they said, okay, everything is good, but current manufacturing cost is very high. So manufacturing revolution should be accompanied together. So otherwise, may not be easy to use this metal lens in the future. So that's true. So we are doing in our post-tech metaphotonics center. So we consider solve this issue. So mainly nano patterning manufacturing. But people may have some wrong thinking. So manufacturing is only related to the patterning, lithography, but actually that includes like a materials selection, materials development. What type of material could be compatible to the current manufacturing scheme, and can you make a new manufacturing scheme or revise the current manufacturing tool to compatible to this metal lens, and also need to consider the design part. The current computing power of the metal lens design is very high because too many metal atom and very hard to design, like electromagnetics and geometrical optics together into the one system. So design should be considered a lot, but in this talk, due to the matter of time, I'm gonna skip the design part. But you can refer to the like Professor Jonathan Fan's work and many other colleague work, how we can improve the design by deep learning, data driven, and many different ways. So I'm going to focus on the material development and nano patterning. So this is a development of our materials selection in the field or community, started from plasmonics. This is a paper from Professor Capasso. And then later, TiO2 was used for visible frequency, metasurface because high N and low K, and gallium nitride follow from Professor Dimping Chai's group. And later, some other materials is developed. But the issue in the TiO2 and gallium nitride is a very good material and perfect. But their fabrication method of ALD and MOCVD, that is quite expensive. So, and also like ALD of like 1 micro thick layer will be a little painful. So easier access like a spin coating or some CBD, simple PCBD, that will be appreciated by the community or industry. So we develop like a tool maybe compatible to this mass manufacturing. So one is called particle embedded resin, resin-based coating, and the other one is like a CBD silicone, but compatible in the shorter wavelengths. So Yeah, this is lithography is main reason is lithography is expensive, e-beam lithography. So people in general, they provide like a imprinting method. It's a very easy way to consider. But typical nano imprinting, you can see the like substrate, functional layer, resist, and molding, and then we have like a sacrificial layer, and you need to do etching or deposition, like a second step process. So this is some example by like modulus printing or nano imprinting making centimeter scale metal lens array. But the problem is we need a high refractive index and low K material, like this one, TiO2 gallium nitride, and thickness is, like a few hundred nanometer level, maybe up to micrometer. So their deposition or etching is not quite comparable to this typical nano imprinting method. So we cannot directly use this method. So we propose some more simple printing method, excluding the second step etching or the deposition process. So this is a simple way. So here is a resin, functional resin called particle embedded resin, and printing, and that's it. That's done. But to make sense of this way, we have to solve the three problems. So can we transfer the sub 100 nanometer pattern by this printing technique? And high aspect ratio is doable or not, and high refractive index, how can you achieve? Because this resin, usually, polymer based one is only, 1.5 is the maximum refractive index. So the first problem, the transfer sub 100 nanometer resolution, we solved by some double PDMS, hard PDMS with the normal PDMS. They have good surface energy, so they can transfer sub 100 nanometer pattern easily. So you can compare with the normal PDMS printing. And aspect ratio is a little many is complicated issue. All the fluidics and so we have to consider viscosity and so on. But anyway, experimentally with some knowledge, experience, we can achieve like a 10 to 1. So recently, we succeeded like a 15 to 1 aspect ratio in the visible wavelength, and then so it's pretty handled by this by some hands-on technique. And the refractive index part is, you can imagine this one is a resin. So to increase the refractive index, we added the functional nanoparticle like a TiO2. So high index nanoparticle, low index resin combination become like a middle of the two materials. So it's from the Maxwell Garnett, like it's effective medium approximation. So finally, depending on their like a ratio, we could achieve up to like 2.0. So that was enough to consider our like meta surface design. And first, the demonstration, we reproduce like even lithography patterned meta hologram by transfer printing by this particle embedded resin and transfer to normal substrate, cobalt substrate, and flexible substrate. So you can see the same holographic image. And then this is the replicated pattern, so little of the distortion, but it's in the range of we can control the phase correctly. So you can see the pretty decent holographic image a few years back. And we transfer this to many different substrate, and we consider how we can consider like a thermal stability and mechanical stability was studied in this work. And later, we first start with the dielectric particle, but later now we can do many different type of particle in different wavelength and like a magnetic material and quantum dot, up conversion nanoparticle, and perovskite. So this scheme can be expanded to many different nanoparticle type of work. So this is our three representative lineup: silicon nanoparticle resin in IR, TiO2, visible, and recent zirconium oxide nanoparticle embedded resin for UV and deep UV wavelengths. So due to the time issue, I skipped this very detailed. But anyway, we made a gas detecting sensor by integration with the particle embedded resin metasurface in PET film. And This is you can see the flexible substrate and integrated with the safety goggle, and this detect gas like toluene benzene by a liquid crystal, so that changes the polarization. So this is a holographic image we can see from this sensor. TiO2 nanoparticle, resin is act very similar to normal TiO2. You can see the holographic image here, and this is the same device, but we made like a normal CBD amorphous silicon. So you can see blue is not covered by the silicon. So later slide, I'll show how we can overcome this the blue range using modified amorphous silicon. So now we have a blue image here with the amorphous silicon. And then this we optimized many different process conditions. So now it's a broad wavelength, and we achieve very high efficiency in the green. So overall 70%, and green itself is a 91%. So there are many good work, but some claim of our advantage is a very simple way. So we just printing, spin coating and printing, that's it. So we achieve like a 91% of conversion efficiency in green. So you can see now holographic image in the very bright ambient light condition, we can observe that. And then this is applied to lensing. So this is TiO2 nanoparticle embedded resin, and we design visible metal lens, but aberration is not corrected. And this is a master mold by e-beam lithography. This is a soft mold in PDMS, and this is a final pattern. So TiO2 embedded the resin structure. So this is a final one. And we made the focusing test, imaging test, and measured this, spot and MTF value. So was pretty close to our expectation. And on the problem is the aberration. So now we try to overcome this aberration issue, making it chromatic. So we succeeded with some design. But the problem is focusing efficiency become very low comparing the previous one. So we thought about immediately. So okay, so achromatic works some way, but not easy. So we rather try single wavelength first. So that was a 2019 work of the image I showed in the earlier today. This is silicon. Silicon is better in the IR wavelength, and we did the same thing, but design with a little larger 4 mm and polarization independent circular the cylindrical design, and some optics the lens value, and same thing. So this is the original mold, and this is a nanoparticle resin, so cluster. So resin is almost gone, so it's kind of clustered nanoparticle, so pretty similar. So little smaller, so it's like a shrinkage of 20%. So this is the lens I showed in earlier slide, and we measure the optical property of this lens. Okay, so past, although MTF value is not 100% of the diffraction limited lens, we measure comparison, normal lens and metal lens. So this is a simple setup, and you can see metal lens provide much higher resolution. So even though this is not a super resolution scheme, their MTF value becomes 6 times larger than conventional glass type of lens. So we have a higher image contrast comparing the conventional lens. So we have a better resolution, but still far away to this, the theoretical limit. So we have to push how to improve this value for some by the lens design and other and so on. And this is we integrate the metal lens into the camera we purchased. So instead of the provided lens, and fully compatible with this electronics. And this is IR source and imaging. This is blood line imaging in IR 940 nanometer wavelength. And now we're trying to do how we can we apply this for biological, like a tissue imaging, or some short, like a skin imaging, and so on. So it's ongoing work. And we tried making some zoom lens by liquid crystal operation. Very, but anyway, bifocal, the modulation of the point by electrical operation. But eventually, it has to go to the very focal and many different like integration with the zoom function and many lens together. And this is a recent UV wavelength range. So we find the zirconium oxide as a good material with high band gap in UV and dim UV. And this is the same design as 325 and 248 and pretty high conversion efficiency. So we did the same thing, zirconium oxide, particle embedded resin, and printing, and show the metal hologram in the two different wavelengths. So we couldn't make a lens here yet because only the problem is UV laser is usually very high power and pulse issue. So the lens itself is damaged or some hard to observe the focusing itself. But anyway, we're trying to solve this problem to making UV and dim UV metal lens in this wavelength. That may help impactful for the tool, inspection tool or lithography in those wavelength as some alternative optical component provided by metal surface lens. So this is a summary of the TiO2 silicon zirconium oxide particle embedded resin. So this is the part of the particle embedded resin. And I have another work. This is amorphous silicon, but engineered by some hydrogen injection and modification of a band gap. So you can compare the ALD, MOCVD, ultra high vacuum CVD. PCVD has a benefit of the in terms of a price and simplicity of the fabrication. So, but the problem is that those amorphous silicon work in only IR range because they are high K. So we found some many literature, the chemist, computational material scientists, they could change some design like band gap engineering, change the atomic structure, so achieve a high end, low K. So basically we can modify the NK value by some way. And we try by very simple approach of the processing. So during the silicon CVD of the silane and H2, and we add some dopant like hydrogen and oxygen and nitrogen. So that can change some value of the refractive index by changing the bonding structure inside of the amorphous silicon. So we can change like a temperature, pressure, gas ratio, and plasma power. And then so okay, this is some final value. So this is like our refractive index of a silicon, and it's usually higher than TiO2 and gallium nitride. But K value used to be very high, you can see here. But this is our modified silicon. So you can see K value is much lower than typical amorphous silicon. So now K value is very close to zero. Blue is still 0.1, 0.08, but still we're trying to making almost to zero. But anyway, now quite comparable to those high index dielectric in visible wavelength. So we have a transparent silicon in visible, and now we can control the blue wavelengths by this modified silicon. So this is the happiest part. And compare the efficiency in green and red, we have can achieve a very high comparable to TiO2, can compare. And blue is was almost impossible, but now we can control blue using this silicon. So now we expand this concept to silicon nitride, so we can control band gap of nitride by the same way, introducing nitrogen, oxygen, and can work this silicon nitride in the UV and dim UV. So, and oxygen also do some function. So oxygen make refractive index a little lower, so sacrifice, but K is go to further, very close to zero. So some game of the combination of this nitrogen, oxygen, hydrogen do something, and we try to understand what's going on in real in atomic structure by TEM and DFT calculation. So it's coming, work is ongoing. So summary, we using this modified band gap engineered material in UV like nitride, visible silicon, near IR still silicon, but performance become much better than typical amorphous silicon. So I hope this two material can be used for our metasurface community. So now, finally, few minutes, I talk about nano patterning. So recently, we make those lineup of high-speed e-beam lithography and ARF deep UV emergent lithography and nano imprinting automated one. So I will show how we can scale up this process by this the combination of the method. So high-speed e-beam, basically nothing special but high current e-beam. So we can make like a large scale master mold comparing like 1,000 times faster than previous typical fabrication. So KRF dim UV lithography first used to achieve like a IR, near IR metasurface, but their resolution is still limited in the IR range. So now this is our KRF lithography pattern for IR metal lens array in 8-inch or 5 mm diameter device. So this is optical property. And now we can use ARF lithography, emergent lithography. So their critical resolution, 40 nanometer. This is our thing. And this is until ARF process, master mold 4 centimeter, master mold by e-beam lithography, typical patterning. And this is a 4 centimeter master mold reticle is used to create 12-inch wafer photo mask. So basically array of this thing, 600 array of a 4 centimeter thing. And this ARF immersion is like a 4:1 reduction ratio. So the finally 1 centimeter metal lens will be made. You can see here. So resolution critical CD is 40 nanometer, pretty comparable to visible. And this concept is now this could be the final device. If you make in the transparent substrate, you can dice one lens, and this can be combined with the nano imprinting I showed in the previous part. And this is just a lithography only, and we can do typical imprinting and do etching and particle embedded resin printing. And this is our new schematic of the resin and high index ALD coating layer. So this is much simpler than this one. So what we did, we do resin coating and printing, and we thin coat of the 20 nanometer ALD by low temperature ALD. So 20 nanometer TiO2 will effectively make entire medium as a TiO2. So this is like a scheme, resin, thin TiO2, but effective property of the entire structure act as like a regular like a ALD TiO2. So we don't need 1 micrometer thick ALD. So rather using just the printing and 20 nanometer ALD coating. So we observed some quasi. We named like a quasi TMT mode. Light is confined only the layer of TiO2. So there is optimal techniques exist. And this is like a transferred to the substrate in transparent substrate 4 to 12 inch. So this is like a resin and ALD coating over 20 nanometer. So those lens performance is pretty good. Conversion efficiency up around 90%. And this is almost the same as ideal metal lens. It's like the metal lens property we can get in theoretical limit, but still this aberration exists. And focusing is perfect. And we used this one for VR, virtual reality demonstration, made like a 4 centimeter large lens and demonstrate like the VR performance. So VR is a little easy, but AL is still a lot of way to go. So we are suffering from the image semi-transparent, like see the outside and then make a correct image here. And so this is a lithography, imprinting, different material will make some like lineup of the manufacturing scheme. So now we are working on automatic line of the printing. We do this roll type of a feeding setup. So it only compatible for flexible substrate like a PET. But anyway, we can make like a continuous scale of a meter. You can see like a roll type of many structure. But in this case, performance will be worse than typical CBD and lithography in the harder substrate, but it has a value for certain application using this, which need a flexible substrate. So this is my last slide. We are working on design. I didn't mention today, but CMOS compatible industry may prefer lithography and silicon-based one and resin coating printing. And this is a scheme of the manufacturing. And immediate application is this short distance LiDAR and this face recognition and AR VR type of optical component. So this related our recent review article. And thank you very much to our student. And thank you very much for conference attendance and conference chair. Thank you very much.